Imagine you could peel back the layers of the universe, every atom, every particle, every invisible current of energy holding existence together. What would you find underneath it all? Well, physics tells us that the entire cosmos is governed by just four fundamental forces. These are the deep underlying rules that shape everything, from the orbits of planets to the fusion inside stars, and even the chemical bonds that make life possible. We have gravity, the force that keeps our feet on the ground in galaxies in vast spinning clusters. Then there's electromagnetism, the force behind light, electricity, and magnetism, which allows you to watch this video right now. And deep inside the atom, we find two more: the strong nuclear force, which glues atomic nuclei together, and the weak nuclear force, which governs radioactive decay. Four pillars on which the entire universe stands. It's an incredibly elegant and powerful picture of reality. But what if there's more? For decades, scientists have wondered if nature might be keeping a secret from us, a fifth force, hidden within the fabric of space-time, waiting to be uncovered. Something subtle, something strange, something that could rewrite our entire understanding of physics. Because if such a force really exists, it wouldn't just change our textbooks. It would change the way we see everything, from the origin of the cosmos to the mysterious dark matter that fills it, and maybe even the ultimate fate of the universe itself. So, how did this incredible idea of a fifth force even come about? Why do some of the brilliant minds in physics believe it could exist? What tantalizing hints have experiments already given us? What could it reveal about the hidden architecture of reality? To understand this, we first need to take a quick trip back in time and revisit the amazing story of how the four known forces were discovered. It's a tale of how time and time again, humanity has realized that what we thought were separate, unrelated laws of nature, were actually just different faces of the same fundamental truth. It all started with Isaac Newton. For him, people saw the force that made an apple fall from a tree, and the force that kept the moon orbiting the Earth as two completely different things. One was earthly, the other was celestial. But Newton, with his law of universal gravitation, showed they were one and the same. It was a revolutionary moment of unification, the first time we understood that a single rule could govern both the heavens and the earth. That was the first fundamental force we truly understood. Then came the 19th century, and scientists were playing with two other mysterious phenomena: electricity and magnetism. They seemed like separate forces. One created sparks and currents, the other made compass needles point north. But then, pioneers like Michael Faraday and James Clerk Maxwell discovered they were deeply connected. A changing magnetic field could create an electric current, and an electric current could create a magnetic field. Maxwell wrapped it all up in a beautiful set of equations showing they were two sides of the same coin: the electromagnetic force. That was our second unification. And as a bonus, its equations predicted that waves of this force would travel at the speed of light, because light itself is an electromagnetic wave. By the early 20th century, we had two forces: gravity and electromagnetism. But as we peered into the atomic nucleus, things got weird. Electromagnetism said that the positively charged protons in a nucleus should fly apart with incredible force. Yet, they were stuck together. There had to be something else, something much stronger, holding them in place. This was the strong nuclear force. Around the same time, we noticed that some atoms spontaneously decayed, a process that didn't fit with any known force. This led to the discovery of the weak nuclear force. So there we were, with four forces. But physicists weren't satisfied. They dreamed of another grand unification, of finding a deeper theory that could connect the strong, weak, and electromagnetic forces into a single superforce. The standard model of particle physics achieved part of this, showing that at very high energies, the electromagnetic and weak forces merge into one electroweak force. It was another stunning success. But the standard model has some big holes in it. For one, it doesn't include gravity. And more importantly, it doesn't explain dark matter or dark energy, which together make up 95% of our universe. This is where the idea of a fifth force gets really exciting. What if there's another force out there that we can't feel, one that primarily interacts with dark matter? Or what if tiny discrepancies in our experiments, like the strange wobble of a particle called a muon, are actually being caused by a new, undiscovered force pulling on it? Recent experiments at places like Fermilab have been studying these anomalies with incredible precision. The results are still tentative, but they hint that something might not be quite right with our current understanding. If these hints hold up, it would be the beginning of a new revolution in physics. A fifth force could be the key to unlocking the secrets of dark matter, to explaining why the universe's expansion is accelerating, and maybe, just maybe, it could be the first step toward finally unifying all the forces of nature into one beautiful, ultimate theory of everything. The search is on, pushing the boundaries of what we know, and reminding us that the universe is still full of mysteries waiting to be solved.
From the tiniest push to the grandest cosmic pull, everything happening in the universe, every single interaction can be explained by just four fundamental forces. But what if there's another one hiding in plain sight, shaping the very fabric of reality? To understand why physicists are searching for it, we first need to understand the four we know. Let's start with gravity, the architect of the cosmos. It's the first force we ever recognized, yet it's the one we understand the least. Back in the 17th century, Isaac Newton gave us a formula that described how gravity works. He realized that the same invisible pull that makes an apple fall to the ground also keeps the planets orbiting the sun. His equation was so precise it could predict celestial movements centuries into the future. But it didn't explain how it worked. Fast forward 200 years to Albert Einstein. He completely flipped our understanding of gravity. He proposed that gravity isn't a force at all, but a consequence of the geometry of the universe. In his theory of general relativity, massive objects like stars and planets actually bend and curve the fabric of space-time. And it's this curvature that dictates how everything else moves. This is why black holes can trap light, and why our universe is expanding. Gravity isn't just a pull, it's the very shape of our reality. But here's the mystery. Gravity is incredibly, unbelievably weak. Think about it. A tiny refrigerator magnet can lift a paperclip, defying the gravitational pull of the entire planet Earth. It also doesn't play well with the rules of the quantum world, the realm of the very small. This strange weakness and its stubborn refusal to fit in with the other forces have led physicists to wonder if gravity's odd behavior is a clue pointing toward deeper laws we haven't discovered yet. Next up is electromagnetism, the force of light and life. For ages, electricity and magnetism were seen as two separate, quirky phenomena. But in the 19th century, a physicist named James Clerk Maxwell proved they were two sides of the same coin. His brilliant equations showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. This beautiful dance gives birth to electromagnetic waves, which we know as light. This single force is responsible for almost everything you see and experience. It binds electrons to the atoms that make up your body. It powers the sun's radiant energy, and it's the foundation of every piece of technology we use to communicate, from your phone to the satellites orbiting our planet. Electromagnetism is both intimate and cosmic, and its unification was a huge hint that other seemingly separate forces might also be connected. Now, let's zoom in to the heart of matter. When scientists first peered inside the atom, they found a puzzle. The nucleus is packed with positively charged protons that should repel each other with immense force, causing the atom to fly apart. But they don't. Why? Because an even more powerful force is holding them together. This is the strong nuclear force. As its name suggests, it's the strongest force in nature, but it only works over incredibly tiny distances inside the nucleus of an atom. It's the cosmic superglue that binds fundamental particles called quarks into the protons and neutrons we all know. And it then glues those protons and neutrons together to form atomic nuclei. The sheer power locked away by this force is what gets released in nuclear reactions, unleashing enormous amounts of energy. Without the strong force, matter as we know it simply wouldn't exist. Finally, we have the weak nuclear force. Don't let the name fool you. It's a quiet giant. This force is the engine of change in the universe. It governs radioactive decay, the process where one type of particle transforms into another. This might sound obscure, but it's absolutely essential. It's the key process in the chain reactions that make stars like our sun shine, fusing hydrogen into helium and fueling the creation of all the heavier elements that make up planets and people. In the 20th century, physicists made another groundbreaking discovery. They found that the weak force and electromagnetism could be described by a single unified theory. They called it the electroweak force. According to this theory, in the fiery high-energy conditions of the early universe, these two forces were one and the same. It was only as the universe expanded and cooled that they split apart, like steam condensing into water and then freezing into ice. This revelation was a game changer. If two forces that look so different today were once united, couldn't the same be true for all of them? This sparked one of the greatest quests in modern physics, the dream of a grand unified theory, a single elegant equation that could describe every fundamental interaction in the cosmos. Scientists began building theories to unite the strong force with the electroweak force, and for a while it seemed possible. But gravity, once again, was the odd one out. Its smooth, continuous, geometric nature, as described by Einstein, just doesn't mesh with the chaotic, jumpy, quantized world of the other three forces. This created a massive chasm in physics, with two incredibly successful but fundamentally incompatible theories: general relativity for the big stuff, and quantum field theory for the small stuff. And it's in the cracks between these two great pillars of science that physicists began to suspect something else might be lurking. A hidden influence, a fifth force that could finally bridge the gap. To find clues, we have to travel back in time to the first fractions of a second after the Big Bang. In the very beginning, the universe was an unimaginably hot and dense soup of pure energy. In this primordial state, all four forces are believed to have been united as a single, perfectly symmetrical superforce. As the universe expanded and cooled with mind-boggling speed, this symmetry broke. One by one, the forces split off. Gravity was the first to go, then the strong force, and finally the electroweak force separated into the two we know today. Each of these separations or phase transitions would have left behind cosmic fossils. We can observe some of them today, like the faint afterglow of the Big Bang called the cosmic microwave background, or the specific amounts of light elements like hydrogen and helium that fill the universe. Some theorists believe that these transitions might have also left behind other, more subtle relics, perhaps invisible energy fields that permeate all of space. And could one of these leftover fields, a faint echo from the birth of the cosmos, be interacting with our world in a way we haven't detected yet? Could this be our fifth force? This brings us to today. The reason physicists are so convinced there's more to discover is that our current model, as beautiful as it is, has some major holes. We have mysteries like dark matter, an invisible substance that has gravity but doesn't interact with light, making up most of the mass in galaxies. Then there's dark energy, a mysterious pressure that's causing the expansion of the universe to accelerate. And we still can't explain why gravity is so drastically weaker than the other forces. Each of these puzzles is a bright red flag, hinting that our standard model of particle physics is incomplete. Perhaps an undiscovered force is pulling the strings from behind the curtain, shaping the cosmos in ways we're only just beginning to guess. In massive particle accelerators and in sensitive deep underground labs all over the world, scientists are pushing the boundaries of what we know, searching for tiny anomalies in their data particle that decays a little differently than expected, a measurement that's just slightly off. Each tiny deviation could be a whisper from the universe, a clue that maybe, just maybe, we are on the verge of discovering a fifth fundamental force of nature. Does a fifth force of nature exist? For decades, our understanding of the universe has rested on four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. They've been tested and confirmed in every experiment. From the smallest particle smash-ups to the vastness of space. But they don't explain everything. And every now and then, a crack appears in this perfect picture, an anomaly. A measurement that's just slightly off, a particle that behaves in a way our equations say it shouldn't. Most of these are just blips, statistical ghosts that fade away with more data, but a few have stubbornly refused to disappear. These persistent puzzles, found in labs and in the cosmos, are the clues that keep the hunt for a fifth force alive. One of the most exciting and controversial clues came from a modest lab in Debrecen, Hungary. In 2016, a team led by Attila Krasznahorkai was studying how an excited beryllium-8 atom decays. They were looking for new physics by measuring the angles between the electrons and positrons that shot out suddenly. They saw a bump in their data at about 140 degrees, a surplus of particles at that specific angle. It was as if the nucleus was momentarily creating a new, unknown particle, which then decayed. Analyzing the energy, they calculated this particle would have a mass of around 17 megaelectron-volts, or about 34 times heavier than an electron. They called it X17, X4, unknown. If this particle is real, it's not part of the standard model. It seems to act like a protophobic bosoner force carrier that barely interacts with protons, but might talk to neutrons and electrons. In other words, a perfect candidate for a fifth force carrier. Skepticism was immediate and intense. But then, in 2019, the same team reported a similar anomaly. This time in helium-4 decays, again consistent with an X17-like particle. Labs around the world are now racing to confirm or debunk this finding. The mystery of X17 remains, but it has reignited the serious, tantalizing possibility of a new force. Another major puzzle comes from one of the most precise measurements in all of physics: the magnetic moment of the muon. The muon is basically a heavier, unstable cousin of the electron. Quantum theory predicts exactly how it should wobble in a magnetic field. Any deviation from this prediction screams new physics. Experiments at Brookhaven National Lab and more recently at Fermilab have measured this wobble with incredible accuracy, and what they found is that the muon wobbles just a tiny bit faster than the standard model says it should. The discrepancy is now at about 4.2 sigma, which means there's only a 1 in 40,000 chance it's a random fluke. What could be causing this? One leading explanation is an unknown particle, maybe a light boson, that carries a new force and nudges the muon ever so slightly. This could be a force that only interacts with muons, or it could even be related to that mysterious X17 particle. Either way, the muon is acting weird, and it might be pointing us toward a hidden interaction. The search for a fifth force isn't new. Back in the 1980s, scientists were already looking for tiny deviations from Newton's law of gravity. In 1986, a team at the University of Washington reported that gravity might not follow the inverse square law perfectly over short distances, hinting at a new force about 1% as strong as gravity, but with a very limited range. While further experiments didn't confirm that specific result, they kicked off a whole new field of high-precision gravity tests. Today, physicists use incredibly sensitive instruments like torsion balances and atom interferometers to probe gravity at every scale, searching for any sign of a fifth interaction. So far, Einstein's theory of gravity has held up flawlessly. But these experiments are constantly tightening the screws, closing in on the tiny, hidden corners of the universe where a new, short-range force might still be lurking. Hints of new physics have also come from our own backyard. In space in the 90s, scientists noticed that the Pioneer 10 and 11 spacecraft, our first envoys to interstellar space, were slowing down ever so slightly more than they should have been. The effect was minuscule, but it was persistent. Some wondered if it was the signature of an ultra-weak, long-range fifth force that only becomes noticeable over vast astronomical distances. Ultimately, a more mundane explanation was found. The spacecraft's own heat radiating away was gently pushing against it. A similar thing happened with the flyby anomalies, where spacecraft got an unexpected speed boost or drag during gravity assists around Earth. While most of these have also been explained by more careful modeling, they highlight a crucial point. Our ability to track objects in space is so precise that even the smallest unexplained drift forces us to question our most fundamental laws of nature. And if laboratory anomalies aren't enough, the entire universe seems to be screaming that something is missing. Take dark matter. It makes up 85% of all matter. Its gravity holds galaxies together, but it's completely invisible. What if dark matter particles don't just feel gravity? What if they interact with each other through their own separate dark force, carried by a dark photon? This dark force might leak out and interact ever so faintly with normal matter, potentially explaining anomalies like the X17 particle or the muon's magnetic moment. Then there's dark energy, the mysterious force pushing the universe apart at an accelerating rate. What if it's not just empty space energy, but the effect of another fundamental field, a fifth force that repels instead of attracts, acting only on cosmic scales? These ideas, often called modified gravity, suggest that the fifth force might be the visible tip of a much deeper structure that unifies quantum physics and cosmology. At the center of this grand search is the particle accelerator, our most powerful tool for peering into the subatomic realm. At the Large Hadron Collider at CERN, every proton collision is a lottery ticket, a chance to discover something new. So far, the LHC has been a stunning confirmation of the Standard Model, culminating in the discovery of the Higgs boson in 2012. But the Higgs itself raises more questions than answers. Why does it have the mass it does? Why is gravity so incredibly weak compared to the other forces? Could the Higgs be a gateway, a particle that connects our world to a hidden sector of particles and forces? Newer experiments like LHCb and Bell, too, are now specifically designed to look for the subtlest of cracks in the Standard Model, searching for rare particle decays that might betray the existence of a fifth force. The line between what we know and what we don't is razor-thin, and a new force of nature could be hiding just on the other side. For now, the fifth force remains a ghost at the edge of our experiments. But history teaches us that the greatest revolutions in science often start with the smallest, most persistent anomalies.
Hey everyone, welcome back. Today we're diving deep into one of the most exciting questions in all of science. Is there a fifth fundamental force of nature? Every so often, physicists find a glitch in the matrix anomaly, a tiny experimental result that just doesn't fit our current understanding. These anomalies are like whispers from the universe. They're not loud enough to shatter everything we know, but they're too strange to ignore. When these whispers appear, theorists get to work. If there is a fifth force, what is it made of? What does it act upon? And why has it stayed hidden for so long? To answer these questions, we have to journey into the wild, abstract landscape of quantum fields, symmetry breaking, and even higher dimensions. We are on a hunt for a mathematical framework where a fifth force doesn't just fit, but is absolutely necessary. So, where could a new force even come from? To understand that, we first need to know how our current forces work. In the language of quantum field theory, every force has a messenger, a particle that carries it. We call these carriers bosons. For electromagnetism, the carrier is the photon. For the strong nuclear force, it's the gluon. For the weak force, it's the W and Z bosons. And for gravity, we think it's the graviton, though we haven't found it yet. These bosons are like ripples in invisible fields that fill all of space. What we experience as a force is just particles exchanging these bosons. So if a fifth force exists, it must have its own field and its own new boson. But this can't be just any boson. It would have to be incredibly elusive, avoiding detection in our most powerful particle colliders, our most precise atomic experiments, and our most detailed observations of the cosmos. All of these have put really tight limits on any new interactions. That's why most theories suggest that if a fifth force is out there, it has to be either extremely weak act over incredibly short distances or be hidden in some clever way. Maybe it only interacts with certain types of particles or only turns on under very specific conditions. Physicists have come up with a few different flavors of new bosons, classified by the type of field they come from. First up, we have scalar bosons. A scalar field is the same in every direction. It has a strength, but no specific orientation. The most famous example is the Higgs field, which gives particles their mass. If another scalar field exists, it could create a fifth force that changes depending on its environment. Imagine a force that's strung out in the empty vacuum of space but gets much weaker inside dense matter, like here on Earth. This could be why we haven't found it yet. The force might effectively hide itself when we're around to measure it. Theories like the chameleon field or dilaton field propose exactly this, and they often pop up in attempts to explain dark energy using new fundamental fields. Next, we have vector bosons. These are more like photons. They have both a strength and a direction. A new vector boson might be a bit picky, choosing to interact only with certain particles, like electrons, neutrons, or maybe even dark matter. This could produce strange effects that depend on a particle's specific properties, like its charge or spin. This is actually one of the leading ideas to explain the mysterious X-17 anomaly, which some experiments have hinted at. The theory is that it is a light vector boson that doesn't like to interact with protons, a protophobic particle. Then there's the dark photon, which is probably the most talked about candidate. It's a theoretical cousin to our regular photon, but it would mediate a kind of dark electromagnetism in a hidden dark sector of the universe, connecting dark matter particles to each other. If dark photons exist, they could occasionally mix with our normal photons, allowing a faint signal to leak into our detectors. This would be just enough to explain some anomalies without completely breaking all the rules of known physics. In this picture, the fifth force isn't some brand new thing, but a glimpse into a parallel world of interactions happening all around us. But what if the fifth force isn't new at all, but rather a hidden aspect of gravity itself? Einstein's theory of general relativity describes gravity as the geometry of space-time, the way mass and energy bend the fabric of the universe. It's elegant, and it works incredibly well. But many alternative theories try to add to this picture, usually by introducing new fields that modify gravity. A popular idea is to add a scalar field that couples to matter and changes the strength of gravity depending on the circumstances. These are called scalar tensor theories, and they often predict a new fifth-like force that's most apparent on cosmic scales but hides when you look at smaller things. For example, Brandstick theory, which was proposed way back in the 1960s, suggests the gravitational constant isn't a constant at all but is determined by a dynamic scalar field. Other models, like FR gravity, tweak Einstein's equations to explain why the universe's expansion is accelerating. Then, you have those chameleon and symmetron theories again, where a scalar field's properties depend on the local density of matter. This allows it to stay invisible in a lab on Earth, but play a major role in how the cosmos evolves. Any of this is right. The fifth force could already be all around us, undetectable in our experiments, but shaping the destiny of galaxies in the vast emptiness of space. Of course, we can't talk about hidden forces without talking about the biggest mystery of all, dark matter. We know it's out there because we see its gravitational effects. But it doesn't seem to interact with light or any of our known forces. So what if dark matter isn't just one particle, but a whole family of particles with its own set of forces? This idea is called the dark sector. In this scenario, four forces we know and love just describe the visible part of the universe. Meanwhile, the dark sector operates under its own parallel set of rules, with its own dark forces and dark bosons. But maybe, just maybe, the two sectors aren't completely separate. There could be portals connecting them, extremely weak interactions. Like a tiny bit of mixing between a dark photon and our regular photon, or between a dark scalar particle and the Higgs boson. These portals would be too weak to see directly, but they could produce subtle, measurable effects in our precision experiments, things like tiny shifts in how particles decay, or small changes to their magnetic properties. And these are exactly the kinds of anomalies that have physicists so excited. If this is true, the fifth force wouldn't just be another item on the list of fundamental interactions. It would be the bridge connecting our world to an invisible one. Now, let's get even more mind-bending. What if the fifth force isn't from a new field or particle at all, but from the very shape of space itself? Back in the 1920s, Theodor Kaluza and Oscar Klein had a radical idea. They suggested that if the universe had an extra, hidden dimension of space, one curled up so tiny that we cue and see it, then electromagnetism could actually be just a part of gravity operating in that higher dimension. It was a revolutionary concept, and modern theories like string theory and M-theory have taken it to a whole new level. These theories propose that our universe might have 10 or 11 dimensions, with most of them hidden from our perception. In these models, gravity might seem so much weaker than the other forces because it is the only one that can leak into these extra dimensions while the others are stuck in our familiar 3D world. If gravity does leak, it could cause tiny deviations from the inverse square law we all learned in school, but only at very, very small distances. This is precisely the kind of effect that many fifth force experiments are looking for. If we ever detect these deviations, it wouldn't just be evidence for a fifth force. It would be evidence for extra dimensions of reality. At the core of all these incredible ideas is one simple, beautiful concept: symmetry. Physicists believe that in the earliest, hottest moments after the Big Bang, the universe was perfectly symmetric. All the forces we know today were unified into a single, indistinguishable superforce. But as the universe expanded and cooled, this perfect symmetry broke, and the forces split apart: gravity first, then the strong force, and finally the weak and electromagnetic forces. The question is, was that the end of the story? Or could there have been one more symmetry-breaking event that we haven't discovered yet? An event that created one last additional field, faint, elusive, and part of a hidden sector, but still influencing the cosmos today. This hidden field could couple to our known particles through what are called mixing angles, which might be so incredibly small that we've only ever caught fleeting glimpses of their effects in those subtle anomalies we talked about, like the X17 particle or the measurement of the muon's magnetic moment. The math behind these theories is incredibly complex, but the message is beautifully simple. Our picture of reality might be incomplete, not because our theories are wrong, but because we're missing one final, hidden connection. If a fifth force is really out there, it would do more than just add a new chapter to our physics textbooks. It would completely reshape our understanding of the entire universe. It could be the key to explaining dark energy and why the expansion of the cosmos is accelerating. It could determine how galaxies form and how dark matter clumps together to create the cosmic web. It might even offer a clue as to why the fundamental constants of nature, like the strength of gravity or the charge of an electron, have the specific values they do. Perhaps they aren't fixed at all, but are the result of a dynamic dance between hidden fields that we are only just beginning to perceive. In that sense, the fifth force would be more than just another discovery. It would be the missing link between the quantum world of the very small and the cosmic world of the very large. All of this theory gives us a mappa guide to the strange and wonderful places where a fifth force might be hiding. But a map is not the territory. To know for sure, we need to test these ideas against reality. And sometimes, the best place to find answers is unten the farthest reaches of space, or in the debris of high-energy collisions. But right here on Earth, because if a fifth force truly exists, its influence might already be all around us. In subtle ways, we're only now learning how to measure. Thank you so much for joining me on this journey into the theoretical unknown. It's a wild ride, and the next discovery could be just around the corner.
But when you think about the frontiers of physics, what comes to mind? Maybe vast, swirling galaxies, or those gigantic, trillion-dollar particle colliders smashing atoms together. But what if I told you the hunt for one of physics' greatest mysteries, a potential fifth fundamental force of nature, is happening right under our noses? It's being fought in the humblest of places. Inside basements lined with lead shielding, on frozen mountaintops where atoms fall in vacuum tubes, and even inside satellites silently orbiting our planet. Because if this hidden force truly exists, it's not just out there shaping the cosmos. It must, at least faintly, be acting right here, right now, within the reach of our technology. And that means we can test for it. The hunt is on, and it's one of the most exciting and mind-bending quests in all of science. So, how do you even begin to look for a new force of nature? The most direct way is to test the one we think we know best: gravity. As described by Isaac Newton, and later perfected by Albert Einstein, gravity follows a beautifully simple rule called the inverse square law. The force between two objects gets weaker by the square of the distance between them. Double the distance, and the force drops to a quarter. It's elegant, it's predictable, and for centuries it has worked perfectly. But every theory that proposes a fifth force predicts a tiny deviation from this law, at least at certain distances. Maybe it's at the scale of a millimeter, or maybe it's over cosmic distances. So scientists decided to put gravity to the ultimate test in the early 2000s. Physicists at the University of Washington's E.T. Wash group built incredibly sensitive devices called torsion balancers. These are modern descendants of an experiment first done way back in 1798. They took tiny test masses made of gold and tungsten, placed them on rotating discs, and then isolated them from literally everything: magnetic fields, temperature changes, even the slightest tremor in the ground. They were looking for any sign, any hint at all, that gravity wasn't behaving as expected at very, very short distances. After years of meticulous work, what did they find? Absolutely nothing. No deviation. Gravity followed Newton's law perfectly, at least down to about 50 micrometers, the width of a human hair. Now, you might think a no result is a failure, but in physics, it's a profound discovery. It told us where the fifth force asterisk isn't asterisk. If it exists, it must either act at even shorter ranges or be incredibly weak, less than 1/10,000th the strength of gravity itself. They narrowed the search, clearing a patch of the map and telling future explorers where not to look. But what if the classical world of spinning disks and weights is the wrong place to look? What if the secret is hidden in the strange, fuzzy realm of quantum mechanics? Newer experiments are taking exactly this approach. Instead of weighing metal disks, physicists are now watching how gravity affects individual atoms. In mind-bending experiments called atom interferometers, scientists use lasers to trap and cool clouds of atoms to just a fraction of a degree above absolute zero. Then, with another flash of laser light, they split the atom cloud in two. These two clouds travel along different paths in a perfect vacuum, fall under the influence of gravity, and are then recombined. Think of it like dropping two identical stones into a pond and watching their ripples interfere. If another unknown force was acting on one path even slightly differently than the other, it would create a measurable shift in the interference pattern, quantum fingerprint of a new interaction. Huge new projects, like the MAGIS 100 experiment in the US and IN in the UK, are building these interferometers on a massive scale, towers hundreds of meters tall. These setups are so sensitive they could detect fifth forces that only affect certain types of atoms or only appear in low-density environments. For the first time, our quantum tools might finally be sharp enough to feel the faint, ghostly tug of a new fundamental force. Of course, we can also look up to the sky. If a fifth force exists, it might subtly influence how things move in Earth's gravitational field. This brings us to one of the cornerstones of modern physics, the equivalence principle. It's the idea, first demonstrated by Galileo, that all objects fall at the same rate regardless of what they're made of. A feather and a hammer fall together in a vacuum. Einstein made this a central pillar of his theory of general relativity. But what if a fifth force breaks this rule? What if it pulls on some materials more than others? To test this, the French Space Agency launched the Microscope satellite in 2016. Inside a pristine vacuum chamber, two perfectly machined cylinders, one made of platinum, the other of titanium, were in a state of continuous, perfect freefall as they orbited the Earth. Scientists on the ground watched their every move with unimaginable precision. If the fifth force coupled differently to platinum than to titanium, one cylinder would lag or lead the other ever so slightly. After 2 years of collecting data, the result was astonishing. The accelerations of the two cylinders matched to within 1 part in a quadrillion. That S, a level of precision so extreme it's like comparing the weight of 2 entire skyscrapers and being able to detect a difference of a single grain of sand. So far, Einstein's principle holds up. Nature seems to obey the rules. But the door is still open. Future missions are being designed to push this sensitivity even further, continuing the search for that one tiny crack in our understanding of gravity. So, experiments on Earth have set tight limits. But what could a fifth force actually explain ? This is where cosmologists get really excited. One of the biggest puzzles in the universe today is dark energy, mysterious. Invisible agent that's causing the expansion of the universe to speed up. Some models propose that dark energy isn't some exotic fluid, but the large-scale effect of a new field that permeates all of space. And if that field exists, it should also manifest here, locally, as a very weak fifth force. This is an incredibly elegant idea. It connects the cosmic with the terrestrial. The same field causing distant galaxies to rush apart could be the same one subtly altering the orbits of our satellites or the oscillations of our atomic clocks. It's a grand, unifying concept, and the hints don't stop there. Researchers have also found tiny, nagging anomalies in other areas, like the way neutrons decay, or the precise magnetic properties of particles called muons. None of these are definitive proof, but they are tantalizing clues. A fifth force could be the missing piece that connects all these different puzzles, perhaps revealing a deeper unity between dark matter, dark energy, gravity, and the quantum world. Perhaps the most precise way to hunt for a new force doesn't involve measuring distance or mass at all but time. We now have atomic clocks, devices so unbelievably stable they would lose or gain less than a second over the entire 13.8 billion year age of the universe. These clocks work by counting the ultra-regular oscillations of atoms, like cesium or ytterbium. Now, imagine a new invisible field permeates space. If this field subtly affects the fundamental constants of nature, like the mass of an electron or the strength of electromagnetism, then the tick rate of different types of atomic clocks could drift relative to one another. For example, a clock based on a cesium atom might run ever so slightly faster or slower than a clock based on a terbium atom. Networks of these optical clocks around the world are now constantly comparing their frequencies, searching for just such a drift. They've reached a sensitivity of parts in 10 to the 18. So far, no confirmed drift has been seen. But these comparisons have placed staggering limits on any potential fifth force. If it couples to normal matter, its strength must be less than 1/10,000th that of gravity. Still, new generations of clocks are on the horizon, pushing this sensitivity even further and turning time itself into our most powerful detector for the hidden dimensions of physics. Beyond all the graphs and data, there's a deeper, more human story here. The search for a fifth force isn't about trying to prove Einstein wrong or tearing up textbooks. It's about a fundamental curiosity, an acknowledgement that nature might have more secrets to reveal. Every new experiment, even one that finds nothing, is a victory. These null results are crucial. They map the edges of the unknown, telling us where we can stop looking and where we need to push harder. And this quest fuels technologies that have a massive impact on our daily lives. The precision of atomic clocks is what makes your GPS navigation possible. The superstable engineering developed for torsion balances informs the design of gravitational wave detectors like LAT. The quantum sensors being built to chase new forces could one day revolutionize everything from geology and navigation to medicine. The search itself, whether it finds the fifth force or not, enriches our world. But there is one final, haunting possibility. What if the fifth force is everywhere, all around us, but it's camouflaged? It could be a force that only changes over cosmic timescales, too slow for us to notice. It might only interact with dark matter, remaining invisible to our instruments. Or maybe it operates in a domain we don't even know how to perceive yet, hidden in the quantum foam of space-time itself. If that's the case, its influence might not show up in any experiment we've yet conceived. But its effects could already be woven into the fabric of our reality, encoded in the fundamental constants of nature. In the way galaxies form, in the very rhythm of cosmic expansion. In that sense, the fifth force might not just be an extra rule of physics. It could be the missing link between the visible and the invisible, between everything we know and everything the universe still has to hide. For now, the Earth remains quiet. There's no unmistakable signal, no confirmed deviation from the laws we know. But in science, silence is rarely the end of the story. It often precedes a revelation. Each unanswered question, each null result, leaves a trail of breadcrumbs, pointing the way for the next generation of instruments and the brilliant minds that will follow. For centuries, we thought we had it all figured out. For fundamental forces that govern everything in the universe, gravity, electromagnetism, and the two nuclear forces. But what if there's another, a fifth, hidden force, silently shaping reality in ways we're only just beginning to suspect? The search for this force isn't just about new particles or equations. It's a journey to the very edge of our understanding. A story of human persistence and the profound belief that the universe still has secrets to reveal. It all started with a revolutionary idea from a man named Isaac Newton. Before him, we thought things only moved if you pushed or pulled them. But Newton introduced something radical, an invisible force, gravity, that could act across vast empty distances. For over 200 years, his single law explained everything from falling apples to orbiting planets. It was perfect. Then, in the 19th century, something incredible happened. Scientists studying electricity and magnetism, two seemingly separate phenomena, discovered they were actually two sides of the same coin. James Clerk Maxwell unified them into one elegant theory: electromagnetism. This was a game changer. It proved that nature's forces could be connected, setting a precedents have been chasing ever since. Just as we were getting comfortable, along came Albert Einstein. He didn't just tweak Newton's ideas, he completely rewrote the rules. In his theory of general relativity, gravity wasn't a force pulling things together anymore. It was the very fabric of space and time bending and warping around massive objects. Matter tells space-time how to curve, and that curvature tells matter how to move. It was a mind-bending philosophical shift. But at the exact same time, another revolution was brewing. quantum mechanics revealed that the subatomic world was a bizarre, chaotic place governed by entirely different rules. Here, interactions weren't smooth curves, but tiny, discrete packets of energy quanta being exchanged. By the mid-20th century, physics was split in two: Einstein's smooth, geometric universe for the big stuff, and the chaotic quantum world for the small stuff. Both theories were flawless in their own domains, but they were utterly incompatible. The dream of a single, unified theory that could explain everything became the holy grail of modern science. Out of this monumental quest came one of humanity's greatest intellectual triumphs, the Standard Model of particle physics. By the 1970s, physicists had successfully unified electromagnetism with the weak nuclear force. This, along with the strong nuclear force and gravity, gave us our four fundamental pillars. The Standard Model has been wildly successful, predicting particles like the Higgs boson decades before its discovery in 2012. It has passed every single test we've thrown at it with stunning precision, but it's not complete. The Standard Model has glaring blind spots. It says nothing about dark matter or dark energy, the mysterious substances that make up 95% of our universe. It can't incorporate gravity into its quantum framework, and it offers no reason for why the fundamental constants of nature have the specific fine-tuned values they do. The search for a fifth force is born directly from these gaps. It's the nagging feeling, the scientific instinct, that we're still missing a huge piece of the puzzle. To find that missing piece, we've built some of the most extraordinary machines in history. At places like CERN's Large Hadron Collider, we're not just trying to confirm what we know, we're trying to break it. We smash protons together at nearly the speed of light, creating tiny fireballs of energy that replicate the conditions moments after the Big Bang. By sifting through the debris shower of exotic particles that live for fractions of a second, we hunt for glitches. For anything that doesn't fit the Standard Model, we're looking for signs of new interactions, new particles, maybe a dark photon that could connect our world to the hidden world of dark matter. Finding one would be the first clue to a whole new kind of force, a portal into the dark sector of the universe. And it's not just CERN. All over the world, from Japan to the United States, scientists are running ultra-precise experiments measuring the properties of particles, like muons and neutrinos, looking for the tiniest deviations from theory that could betray the existence of a fifth force. Throughout history, the biggest leaps in physics have come from these tiny deviations, anomalies that just wouldn't go away. The strange orbit of Mercury didn't fit Newton's laws, but it was perfectly explained by Einstein's relativity. Tiny shifts in the energy levels of hydrogen atoms seemed wrong, until quantum mechanics gave us a whole new way of understanding matter. Today, similar anomalies are piling up. The muon G2 experiment at Fermilab, for instance, has found a persistent, tiny wobble in the way muons behave. A discrepancy that suggests some unseen force is nudging them. Meanwhile, researchers in Hungary have reported a mysterious bump in their data, the X17 anomaly, which could point to a completely new particle, a potential carrier of a fifth force. While none of these are confirmed yet, they are the cracks in our current understanding, and it's by exploring these cracks that the next revolution in physics will emerge. Behind every collider, every equation, every anomaly, there are people, scientists, driven by a unique blend of wild imagination and painstaking discipline. They have to dream up ideas big enough to rewrite our understanding of reality, but also be ready to see those dreams shattered by a single decimal point. It's a world of incredible highs and frustrating lows, where a tiny calibration error can invalidate months of work, but a small, unexpected signal can change everything. These scientists are part of an unbroken chain, stretching back centuries, all asking the same fundamental question. Why is the universe the way it is? And that question isn't just intellectual, it's deeply personal. Because every discovery, big or small, gives us a clearer glimpse into the grand architecture of existence and our own place within it. So, where does this leave us? The hunt for the fifth force highlights the great paradox of modern physics. We've never known more, yet we've never been more aware of how much we don't know. We have the math to describe how the four forces work with incredible accuracy, but we have no idea why there are four, or why they have the properties they do. Some physicists think a fifth force could be the key to uniting gravity with the quantum world. Others believe it will unlock the secrets of dark matter and dark energy. Whatever it turns out to be, its discovery would be a moment that redefines science, ranking alongside the discoveries of Newton, Maxwell, and Einstein. It wouldn't just be a new chapter in physics, it would be a new way of seeing reality itself. The story of forces is the story of us learning to read the universe's invisible language, and right now, it feels like we're on the verge of discovering a whole new letter in its alphabet.
For all of human history, the universe has revealed itself in layers. Each new discovery has pushed back the boundaries of what we call reality. Gravity showed us that all motion is connected. Electromagnetism revealed the deep unity of light and matter. Quantum physics unveiled the hidden, shimmering texture of existence itself. Now, the possible discovery of a fifth fundamental force may represent the next great leap in that lineage. This isn't just another chapter in a physics textbook. It's a potential turning point in our understanding of what the universe truly is. The new frontier of physics isn't a place of thunder and lightning. The fifth force, if it's real, is a whisper in the equations, a tiny shift in the 11th decimal place. And in the coming decades, this whisper will be hunted by a new generation of incredibly sensitive tools. Imagine atom interferometers stretching for hundreds of meters deep underground, or space-based torsion balances operating in the perfect quiet of microgravity. Think of neutrino detectors that can register a single particle from a distant cosmic explosion, and quantum sensors capable of mapping gravitational gradients at the atomic level. These experiments will achieve a level of precision that was unthinkable just a decade ago. Meanwhile, at places like CERN, the high-luminosity Large Hadron Collider and the proposed Future Circular Collider will smash particles. Together at ever higher energies, they'll be searching for new bosons, exotic fields, or dark photons that could be the messengers of interactions we've never seen before. At the same time, cosmology is entering its own golden age of precision. Space telescopes like Euclid and the Nancy Grace Roman Space Telescope will map the structure of the universe with such breathtaking accuracy that even the most subtle deviations from Einstein's theory of gravity could become visible tiny ripples in the cosmic web, hinting at a hidden force guiding the evolution of galaxies. The fifth force might not be found in one grand eureka moment, but in 1,000 consistent whispers data points from all over the world, aligning into a new pattern too coherent to be ignored. The greatest promise of a fifth force lies in the dream of unification, the idea that it could finally bridge the divide between the four forces we already know. Picture this. What if the fifth force arises from a new field that permeates all of space? A kind of cosmic background that links the strange world of quantum physics with the grand geometry of spacetime. It could be the missing mediator, allowing gravity to finally speak the language of quantum fields. If that's the case, it might complete the century-long quest to reconcile general relativity. In quantum mechanics, a dream that has eluded physicists ever since. Einstein first tried to merge his equations with the quantum world. Some of our most advanced theoretical frameworks already point in this direction. In string theory, extra hidden dimensions could naturally give rise to new forces that appear incredibly weak in our everyday four-dimensional world. In loop quantum gravity, where spacetime itself is built from discrete quantum loops, residual interactions between these loops could manifest as new, subtle forces. Even more radical are proposals linking the fifth force to quantum entanglement. These ideas suggest that what we call forces might not be transmitted through space at all, but are instead manifestations of deep, information-based connections woven across the fabric of spacetime. If any of these ideas prove true, we might finally understand not just how the universe operates, but why its laws take the specific form that they do. For decades, two of the greatest mysteries in all of science have refused to yield: dark matter, the invisible mass that holds galaxies together, and dark energy, the mysterious pressure that's accelerating the expansion of the entire universe. Could both of these cosmic puzzles be different manifestations of a single fifth force? Some theories propose that dark matter particles interact with each other through their own dark version of electromagnetism, a force mediated by a dark photon. This would explain why dark matter clumps together under gravity, but seems to behave so differently from the ordinary matter that makes up you, me, and everything we see. Other theories suggest that dark energy arises from a slowly evolving cosmic field, one that changes the very energy of empty space over billions of years. If true, this field could subtly alter how gravity behaves over vast cosmic distances, effectively acting as a repulsive fifth force that's pushing galaxies apart. In either scenario, the fifth force wouldn't just be a small addition to our current model of physics. It would be the missing link connecting the visible universe to the invisible one. It could finally tell us why the universe expands the way it does, why galaxies form in the patterns we observe, and perhaps even why the cosmos seems so perfectly fine-tuned for complexity and ultimately for life. In essence, it could answer the deepest question in modern cosmology: why does the universe look this way and not some other way? Every time we've gained a new understanding of nature's forces, it has completely transformed civilization. Mastering electromagnetism gave us electricity, radio, and the entire digital world. Harnessing the strong and weak nuclear forces gave us nuclear energy and powerful medical imaging, even gravity. Once a purely theoretical concept, now guides everything from aircraft and GPS satellites to our new gravitational wave detectors. If a fifth force exists, no matter how faintly it acts, the technologies we build to detect it will reshape science itself. The quantum sensors, ultra-stable atomic clocks, and experiments with ultra-cold matter being developed for fifth force research are already revolutionizing fields like measurement, navigation, and materials science. And the future spin-off technologies could be even more incredible. Imagine subatomic accelerometers that can detect underground water or mineral resources without ever having to drill, or quantum gravity detectors that could provide early warnings for earthquakes, or field mapping satellites that could determine the composition of a distant planet from orbit with atomic precision. Just as Einstein's abstract theory of relativity eventually gave us the GPS in our phones, the search for a fifth force could one day power tools and applications that we cannot yet even begin to imagine. Every major shift in physics has forced humanity to rethink its place in the cosmos. Newton taught us that we live in a predictable, clockwork universe. Einstein showed us that time and space themselves can bend, stretch, and flow. Quantum theory revealed that uncertainty and probability are woven into the very fabric of existence. A fifth force, if we find it, could trigger the next great paradigm shift. It could move us from a universe governed by four disconnected interactions to one unified by a deeper structure. Structure perhaps rooted in information, geometry, or something even more fundamental. It would be a profound reminder that the laws of physics are not fixed, absolute truths, but are our evolving approximations of an ever deeper order. And if this fifth force is indeed connected to the dark sector of the universe, it would mean that everything we see, the stars, the galaxies, the planets, even ourselves, is only a tiny fraction of a much grander reality. The cosmos we experience would be just one visible thread in a vast hidden tapestry of unseen fields, invisible energies, and perhaps even parallel layers of existence. But even if a fifth force is never confirmed, the pursuit itself is one of the purest expressions of human curiosity. To spend entire careers searching for something that may not even exist, to dedicate years to refining equations, building detectors and analyzing data for anomalies smaller than the width of a proton is an extraordinary act of faith in the power of reason. It shows that we, as a species, are not content with knowing only what is visible or convenient. We are driven by an innate need to ask why and to keep asking, even when the universe answers only with silence. But that silence is also meaningful. Every null result, every experiment that finds nothing, tightens our grasp on reality, narrows the space where our ignorance can hide. It's a powerful reminder that discovery isn't just about finding new things. It's also about understanding what remains consistent, what endures, and what makes the universe coherent in the first place. One day, perhaps the signal will come, a subtle deviation in a measurement, like the tiny resonance peak where there should be none. A drift in atomic frequencies that no known theory can explain. And when that happens, the scientific community will not celebrate an end, but a beginning. Because every new force, every deeper law, opens up a whole new universe of questions. What are its particles? What symmetries define it? How does it fit into the grand story of the cosmos, from the Big Bang all the way to the birth of consciousness? When the fifth force is finally understood, it may not just complete our standard model of particle physics, it may dissolve it entirely. It's revealing that what we thought were separate forces were just shadows of a single, unified interaction. The fifth force might not be just one more among many, could be the very foundation beneath them all. We have measured our world with astonishing precision. We have mapped the four forces that shape every star and every atom. And yet the equations still whisper of something more. A missing symmetry, a hidden field, a force that binds what we cannot see. The fifth force may not reveal itself easily. But the search, that endless, unyielding curiosity to look beyond what is known, is itself the most powerful force in nature. It's the force that made us aware of the universe, and the one that may one day help the universe understand itself. Thank you for watching. If you found this journey to the edge of knowledge as fascinating as I do, please like this video and subscribe for more explorations into the biggest questions in science.